Okay, so we are all I am going to summarize CUDA with another example, and I will just close CUDA discussion. We didn't do, I did simple problems and simple ideas, but you should be able to program now in GPU with this idea, simple ones. We want to keep simple, and if you want to take up a complex problem, then you need to read and you need to experiment. In fact, a lot of it is experiment. So, the technology is not saturated, so that everything is streamlined. So, finite difference, derivative calculation using finite difference method, which is project for quite a few of you. Okay. So, I will do that problem with the CUDA. This is a good reference, you can just look at it, and this book is, the solution is from the book. I have taken the program from the book. This is a website. So, what is finite derivative? Second order derivative using finite difference method. So, I will illustrate by second derivative. Okay. You can do for any derivative, idea remains the same. So, we will use central difference scheme, where you take 3 points and compute derivative to the midpoint, second derivative, and the formula is this. So, u I plus 1 minus 2 u I at this. So, I am computing derivative ith point. So, point in the right minus twice the point at the same location plus point in the left, value of the point at the left, divided by h squared. Okay. So, please keep in mind that when this guy is taking derivative, it needs the values of the left and right guys, which is not the best thing to do for GPU. You understand, every thread would like to do its operation locally. It is not in a, like memory is not shared for threads. Threads have their own registers, well, not in a direct way. We have to think of ways to make sure that this operation can be done by all the threads. Example which I gave, the simple examples are Ci equal to Ai plus Bi. This is great, because every thread has Ai and Bi and Ci, right. But now I need value of the left thread and right thread. So, there is a, so it would have been nice to do if every thread is independent. This is very critical for GPU programming. You would want to write in such a way that you need value of the same thread. But right now these guys are talking to left and right. Okay, this guy is taking left and right, and that will cause. So, what should the GPU do, or what will the thread do? If you do not have the variable, then you go to the main memory. If I do not instruct it properly, then it will simply go to the main memory, which is global memory, global of the GPU. GPU has its own memory, please keep in mind, GPU and CPU. Please do not mix up, the host memory is not, you do not want to go to the host memory at all. Yes, so this is one remark which I want to make it very emphatically, that for GPU programming, once you copy from the host, then be in the and well, device has a data now, do not go back to CPU. Going back and forth will just destroy the performance. The final result should be copied to GPU, a CPU host. So, if I am doing finite difference method, then I should iterate this loop inside the GPU only. Okay. And once the final result is computed, final time, then you can go back to CPU. In fact, we need to go back to CPU, because CPU can write the data on the hard disk. This I did not tell you before, GPU do not have access to the hard disk. GPU is a accelerator, GPU is an assistant, but great assistant. It can do computation very fast compared to the main CPU. Okay. So, this kind of operation is not great for, right now if I just do it with the thread, is not going to be efficient. Thread parallel operation not possible, interdependent threads. So, get data from the global memory, that is what it is going to do, and poor performance. So, the code is pretty simple. So, let us look at the code, the one which simple implementation which is not efficient. So, I have this data is d in and size of the array and float, that is straightforward. So, my result is d out, which has the second derivative. So, what is the formula? First get the array index, the global array index, because I need to go to the global array, right. So, it is thread id dot multiplied thread id plus block id into block dimension. Data is 1 d. Okay. So, this is the global index for the variable. So, in this array it may be divided in blocks, but I will represent the location in the global array. So, I get I. If I is greater than size, this is a check which is good to keep return. So, that will try to access memory which is outside the array. Otherwise, I say this my result is array I minus 1 minus 2 dot f is 2.0, 2 d in plus d in I plus 1 divided by h squared. Okay. And this function will return to the main function, and it will have the results. So, main is also easy. So, we create this in and output by CUDA malloc. So, I am creating them inside the GPU, and CUDA mem copy into d in. So, there is some more stuff here. Okay. I mean, input array has to be created, no. So, into d in, and we understand mem copy, and this is the kernel, DD kernel, double derivative kernel, and I explained why I should choose the block size as this. TBP is thread per block, this is thread per block, and so this we discussed this in the earlier class. So, you need to give the block and the thread, and number of threads and number of blocks, and arguments are d out, d in, n and h. Okay. Then my result is back from d out to out, and I print it. Okay. I did not put the print statement here, or well, I will not print the long array, but my result is here now. What I can do whatever I want to do. Of course, we are not going to use GPU for computing derivative of an array for one time. It is not the great, it is very bad, I mean, for why do you want to write a CUDA program if I want to compute derivative only once? I just use Python and done. Of course, this is part of a bigger problem like finite difference method for solving CFD problem. So, but this is an illustration. Okay. So, how do I make it efficient? Any suggestions? So, please keep in mind that when it wants the thread I wants data, of course, at I, but it also wants for I plus 1 and I minus 1. So, where does it get data from? It goes to the global memory, and each time thread goes to global memory, it is time consuming. The fast memory is register and shared memory. So, what is the obvious solution? Keep the data in the shared memory. Okay. So, this is a block, whatever data is needed for this block, I will keep in a shared memory. Okay. Only problem is that for computing the derivative at point here, I need data in the other block, right. So, I need to do some extra padding on my shared memory, and that is the only difficulty, otherwise it is trivial. So, this is my array, I divide in 4 blocks, and my data, let us think of the block 1, okay, this block. This block I have only, for illustration I keep only 4 numbers. Okay. Now, so shared array, you may think, okay, I need only 4 numbers, but that is not true. I need 6 numbers. Why 6? Because I need one in the right and one in the left as well. So, these are the numbers which are added. This is the variable I am using is called radius. Okay. So, we have the required data plus one more. For central difference scheme I need one more. So, radius equal to 1. So, this is 1 in the right and 1 in the left. For second derivative we need only one radius, no, 1 in the left, 1 in the right. Okay. So, that is what we have, number minus 1, which is left number, and this is a number in the right, 4. But okay, so let us look at the code. Anyway, so this is pad left and right, and fill the leftmost and right. Okay. Now, there is one more point. Yeah. So, I need to fill. So, this is called stencil. Huh? So, this is another word called stencil. This is a word stencil, and these guys are called halo. You know, you seen halo behind a head, no? So, head plus surrounding. So, that is called halo. Okay. Now, let us look at the code. So, this is a function which looks pretty long, but it is not. I mean, these are this involves some condition. Okay. So, let us first look at, let me tell you what condition is required. For the end point here and here, this guy, when I come here, my shared array has only 5 elements, 6 here. Okay. So, this special case, what value should I put? Because this array is not, this value is not available in the array, right. I mean, array I give only 16 numbers, but I need the value here. So, that we need to make a guess. Okay. So, the end points, both left end and right end, are to be taken care of by the programmer. The value is not available, and that is why these conditions are here. Okay. I am going to come to that in a minute. So, let us look at the arguments, which is d out, output, d in, this is same as before, size and h. So, this was global array address, and now I create shared memory, const int s. So, this external shared s in. So, this is my name of the this array is s in, s in. Okay. And I am going to keep filling in s in. So, and the index for this array. So, but C array index has to be, cannot be negative, huh? That is another issue. C array index cannot be negative, Python index can be negative, okay, but not C array. So, you have to renumber them. So, when you renumber them, I am adding RAD, and RAD has been defined earlier, okay, RAD has defined earlier, RAD equal to 1. So, minus 1 becomes 0 and everything is shifted to the right. Well, we need it because that is the syntax of C. So, I need to copy my array A into Sn, shared location. So, what should I do? What should be the value here in shared? It should be the first array. Okay, this is the first array. By the way, please keep in mind that this program is executed by everybody, every thread. So, I am not doing a loop. This is executed by an array, by a thread whose index is I. Okay, this is one, when I started looking at this code, the first time I was confused. What is this? Where is, what is I doing there? Why there is no loop? But this is executed by every thread. But the number of thread can be more than cores. That is not a problem. You have a thread which is execute its own job. It does not care about the neighbor, it just does its job. So, d a and I, so this is a variable here. So, maybe I should, yeah. So, this is a variable location. I use some other color. This is my variable. Okay, this variable. Its index is 0. Where should it go in the Sn? It should go to this location, because my left guy, this is reserved for this variable. So, it should go to one shifted to the right. So, S I d x when I equal to 0, S I d x will be 1, because S I d x is always thread I d x plus RAD. Well, actually it is not I plus 1, no? That is another problem. I for this one is what? I for this guy is 4, but what is thread index for this object? 0. So, shared memory I had to go to 0 plus 1. I should not go to 4. The shared memory is local to every block. So, this block, this is the shared memory for block 1. I have shared memory for block 2, separate shared memory. I hope this part is clear. So, the shared memory is being filled up. The obvious thing is to just fill these 4 numbers. They are filled as 0 to 3, but the array index for the shared array is 1 to 4. Is that clear? I mean, I am belaboring this point. So, this index is 1 to 4, but my thread index is 0 to 3, okay, and is being done locally in the block. It is not going outside. Now, let us look at what happens when thread ID is 0. Okay. So, basically the I equal to 0 does one more work. It is copying, of course, its own value in the shared array, but is also copying, it should also copy the left guy. Okay. Somebody has to do the work, this extra work. So, the shared the thread 0 copies 1 in the left to shared memory 0. So, this is what it is here IDX minus RAD. So, for this location what is IDX? SIDX? SIDX is 1 right 1. When thread ID is 0, then SIN is 1. So, I want to fill the left guy. So, what should I do? So, thread SIN minus RAD. Okay. So, SIDX minus RAD. What should be the value to be filled? D in I minus RAD. So, I is the index for this. So, I go 1 into the left. So, I minus RAD. Okay. This will come from global. Not everything can be done by locally. So, this will come from global, because that is not available inside the block. So, this will be global. But my numbers of variables in a block are many. Number of threads is 1024 or 512. So, one is 1 by 1 in 512. So, it is tolerable. Now, this is one case, but what happens when I am here? So, that is corresponds to block 0. So, what should it fill? It does not have I minus RAD, in fact, it will give an error. For this guy I minus RAD will be a minus 1 and D in minus 1 does not exist. So, what should I do? I will make a guess. Okay. So, my function is the main program uses sine function. Okay, I know it. So, for sine function my data is going like this. By the way, it is also a good idea, you should keep in mind in finite difference or even for any simulation is periodic box. If you are using, then do not put both left point and right point of the periodic box, because next box will start like this. So, this point is repeating, right. So, if you calculated iteration or you are iterating this point, you should not iterate this point, because that will be, there can create some ambiguity. Okay, one student should have only one roll number and his solution should be clearly defined. So, this point is not stored in for periodic box, the rightmost point, and keep from here to one point to the left. Now, what should I make a guess? If a odd function near the edge, then I should say, well, value here which is minus 1 is a value at 1 with a negative sign. Okay. So, that is what I put here, minus IN I plus 1, I plus 1 is 1, 0 plus 1. Okay. So, I chose that. Okay. I know the value of the function. Safe thing to do, which is often done, is set it to same as what is value here, but that has a problem, here it has a cusp, and cusp first derivative becomes discontinuous, right. First derivative is 0 and positive, 0 from the left and positive from the right. So, that is not a good thing to do. Anyway, this part is up to you. So, I chose minus D of 1. Same thing we need to do the right point. Well, for when my I equal to size minus 1, well, thread ID is block dim minus 1. So, my this is corresponds to this ID, this guy, block dim minus 1, which is the last point, right. 4 minus 1 is 3. So, it will copy, it has already copied this one, this operation has been done, but now this has to be copied. So, if it is not the last block, then I can just take this value d I plus rad and copy the I plus rad, I plus 1 I copy. But if it is the last block, which is I equal to size minus 1, okay, this number, then what should I do? I need to extrapolate again, and well, I know for sine function this is 0, the last point is 0. So, I have put it 0. So, this function works well. Finite difference method always gives some error, but you can run this code in Colab. You will find the double derivative is following the same as sin x with k squared in front. Okay. I think k is 1. So, double derivative is same as the function itself to good precision. And after this is done, then I need to add one more important thing. This called this object S thread sync thread. Why sync thread? Because every thread is doing its work, all the workers are doing their work, but some of them may be doing quicker than others. And imagine that I do this computation derivative and not all this, at least these edges are not updated, then I will get error, right. I mean I will not get the correct value. I want my shared memory to be filled properly. Yes. So, I should have finished job up to here, every thread should have finished the job. How do I ensure that? I should sync all the threads. So, sync thread means when you come here, you just wait for other guys to also finish the work. So, you can take a smoke if you have a cigarette or take some water. Okay. So, this is the point where every thread is told okay, wait until everybody is finished. After that I can do this operation u I plus 1 minus 2 u I divided plus u I plus 1 divided by h squared, that is it. So, this is something which you need to do with derivatives and you need it for your project. I think next slide is the main function, which is just straightforward. So, this is a call. Okay. So, I need to create the array and the function will do the rest. Okay. What about 2D? So, 2D my padding has to be done for each block, both up down and sideways, left right. Okay. So, this is my array of the block. So, please keep in mind that I have divided this data into many blocks and please write a code for more blocks. So, then for every block, this block has many threads, every block will have a hello, right. So, this hello has to be filled by its I need to fill the hello of this object by its neighbors. Now, that is a tricky part for 2D. 1D of course, I had only left neighbor and right neighbor, but now I have a lot of neighbors. So, this is an interesting exercise. If you are not doing a project, then also you can try to do this operation. So, create the shared array and fill up these numbers. Okay. It is a good idea to use the grid, no, because grid will give you x index, y index, and that will help you to write the cleaner code. Okay. Please keep in mind that the data is basically 1D data, the 16 numbers. So, your hello will come like that in between, because you see for this the hello is this one to the right, let us say this one, then it comes to the left, it is another hello, but then there is the data, then two hellos again, and with 1D it is tedious. I would not want to write the code with just 1D array. So, I will use a block. I have not written it, but I advise you to write this code. I do not know how many of you like this coding part. It is intellectual fun, it is like a puzzle. So, and it is also a slightly different game than a theory problem, or is mathematics, well, is different than a physics puzzle. Okay. Here one thing is, if a code does not work, it gives you a wrong error. In theory, you do not know how to test it typically, right, whether your solution is right or wrong, your idea is correct or not correct. You can test it immediately, but here you can test it right away. So, there is a famous person, Strauss Troop, how you put his name, who C++ designer. So, he says that if you written a code for a certain problem, then you understand the problem very well. So, if you have an algorithm in your head or in even written in paper, but until you write the code, you have not fully understood it, all the nuts and bolts. So, I think that is I like that statement. If you want to understand it well, you program it. Okay. So, yeah. So, this is I want to say that for 3D or even 2D, you should use a block, grid, actually dim block. So, this is going to be our block is 4 by 4, and so this is a 4 by 4 block, but my stencil is 6 by 6, right. There are 6 numbers, this is 6 by 6. Okay. So, fill the stencil in a 2D grid, and also for 3D, well, 3D will be cube. So, then it is more complex, but it is going to 6 by 6 by 6. Okay. So, we can also do for 4D. Okay. So, whether 4D is not unusual. Okay. So, 4D is used in field theory, and there are, you can think of Ising model in 4D. Okay. Okay, now summary. So, how to use GPUs? So, question mark. So, use many threads for parallel execution, and they should be independent. Of course, you cannot obtain this independence all the time. For example, finite difference method, they are not independent. Okay. So, you have to use shared memory for that case. Thread employs registers which are fast. For collective action like sum, use shared memory, or also for derivatives I showed you, you need shared memory. Avoid accessing the global memory. Keep looping within the GPU itself. Okay. Keep looping within the GPU, and if possible you only get the data from host, compute everything, then go back to the host. Okay. That is ideal, but once in a while you need to write your data to the hard disk. Okay. So, there is one more thing for HPC, this is very simple observation, but you should keep in mind. Some of you are already writing HPC codes. So, I have this main program. So, I read my input, then my output is somewhere here, means final, the program ends here, output. So, if I read a field for finite difference method, I should read it here or create it here, and I need to write the field. Why do I need to write the field? Because I need to visualize how the velocity field looks like, electromagnetic field looks like. Also, when I may say that I want to continue from this initial condition and I go further, correct? I mean, it is possible, no? I mean, weather codes, I get the weather prediction for today, but then I can use the same data to predict for tomorrow or day after tomorrow. Okay. So, this output field can become input for the next run. In fact, typically it does, but in between I may have to write some global quantities like energy. So, some in between, no, I need sum of u squared. Then what should I do? Should I go to the global memory or what? Because the energy will be updated here. So, I need to output. So, should I go to global or not? No, do not go to global, because global will basically give very poor performance. For one number you never write to global, you create a buffer. So, you can create a buffer. Buffer is temporary location, temporary storage, and buffer can be, let us say size 100 or 1000, and here you store energy at different times, this energy. So, you can store 100 times if size a buffer of size 100, and then when you are writing the field, that time only you write output your buffer. So, there are nice ways to do it. When buffer full, it automatically writes to the global memory, but we need to keep, I mean, this is a very important observation, we should implement it in your codes. For testing you do not need to worry, okay. Testing you do not put buffer right away. First test you just output on a global memory, no problem. Do not make the code efficient at first time itself, that will be create bugs. Buffer you can store in shared memory or okay. So, you can keep inside the block itself in shared memory, or okay, there is one more point. So, let me just make this clear. Some buffer you can share it, let us say block 0 is keeping all this energy stuff, but even if you do not want to keep in the shared memory, you can keep in the buffer of the global memory, but do not go to the memory of the host. So, when I say that write this data it is written in the host memory, and that goes to the hard disk. So, that is not what you should do. Do not go to the host memory and hard disk. Global memory is okay. So, this energy I could write to global memory. So, this buffer can be created in global memory. So, you understand, I mean, this is slower, but is not as slow as accessing the host memory. Mem copy avoid as far as possible, except first time and last time. Okay, avoid on host memory. Okay, so let us just make a comparison. Okay. So, multi-threading in OpenMP, which I have not done it yet, but I will do it soon. MPI, and this also includes multiprocessing for for Python, MPI and CUDA. So, there could be more differences, but I have listed main ones what I believe. So, for multi-threading OpenMP, number of threads is less than equal to 100. Okay, so I think I should remove this multi-threading only. Okay. MPI, number of processes within a node is less than 100, within a node. Okay. Within a node there are 2 processors, okay, and each processor may be 32 cores or 64 cores. So, number of processes will be around 100 maximum. If you have 2 Rome processor, then it is going to be 128. But CUDA can have how many threads? It would 10 power 6, 10 power 8. So, you can create huge number of threads, okay, also 10 power 8 possible. So, for multi-threading I use for loops, is quite common. I mean, if we did that in the example, I divide the data among threads. So, my array is, let us say, size 10 power 8, then I divide it into 4 processors or 4 threads, and I need to loop for 10 power 7 times 2.5, so that big number. Okay. So, these are done by loops. An array is physically divided into in memory, but in CUDA, in fact, we like each array variable to be a thread if possible. Okay. Sometimes it may not be possible, but each guy should be a thread. In fact, we should you would want to do that. 10 power 9 threads, okay, you create that, and they are handled by thread ID and block ID, no loop. So, cache miss is common, okay, but examples, there was no cache issue except one time, there is no cache issue really, but false sharing or not false sharing. False sharing is possible, which I did not discuss. Also, we need to do a lock. If same data is being accessed by more threads, then we need to put a lock, atomic. So, this is one thing you need to be bit careful. All the many threads accessing a same location. So, reduction variable like sum is a global variable which use when some local sum is put a sum, and we did this for multi-threading, okay, and that is where again we had this atomic issue was there. But here this variable like sum will be part of shared memory. You do not put in global memory, and shared memory is fast. I should also make a remark, I think I did that. The memories of GPUs are the fastest, they are DDR6 in AMD. Yeah. So, these memories are very fast, and typically if you look at servers, they are DDR5, double data rate. Okay, these are like higher the DDR, faster it is. So, GPU memories are fast, even the global memory is faster for GPU than CPU. Okay, shared memory is very fast. Okay.